our project on the design of automatic water tap control using PLC technology. In this project, we have focused on integrating mechatronic systems with PLC to create an efficient and intelligent water management system. Our goal is to design an automatic tap that not only conserves water but also provides ease of use through automation. Our group consists of 5 members as per listed. Let's overview our presentation roadmap. We start with an introduction outlining the study's background, the problem we're addressing, and our objectives. The literature review follows where we examine existing water tap systems, PLC integration, and related ladder diagrams. In the methodology section, we'll discuss our design process, selection, and evaluation. Our results section will feature the systems, block, and ladder diagrams detailing our project outcomes. We then explore applications for our automated water system, considering its practical uses. We'll wrap up with conclusions, summarizing our findings and potential enhancement to our design. Let's dive in. In our project, design of automatic tap control, we focus on innovative sensor taps that not only conserve water but also elevate hygiene by minimizing cross-contamination risks. These taps are crucial for sustainable water management in a growing world and play a vital role in preventing disease spread, a lesson underscored by the recent pandemic. The design of automatic tap control project tackles the pressing issues of maintaining hygiene and conserving water. Our automatic taps reduce the risk of spreading germs by limiting touch, save water by shutting off when not needed, and provide accessibility for those with disabilities. Our design of automatic tap control project is focused on creating a tap system that not only conserves water and reduces time spent at sinks, but also minimizes congestion and manual touch points, thereby enhancing safety, minimizing space, and giving us a deeper understanding of PLC-based automation in tap systems. In this section, we'll cover our methodology focused on 3 primary areas: concept design, design selection, and design evaluation. We'll see how each stage leads to the development of an optimized automatic water tap control system. Sphere of water tap systems, innovations span from Veni and Srinidhi's Arduino-based remote control taps to Fitria et al.'s IR sensor-activated automatic faucets. Additionally, Hulukati et al. Have introduced solar-powered taps with ultrasonic human detection, marking significant strides in water conservation technology. Programmable logic controllers or PLCs are the backbone of our design of automatic tap control project, evolving since 1968 to become essential in process control and automation, interfacing with a variety of signals and programmable through intuitive ladder logic diagrams by engineers. Ladder diagrams are a key element in our design of automatic tap control project, simplifying the programming of PLCs for logical operations and enhancing their flexibility in managing our automated systems.
Moving on to the session, we will cover our methodology, focusing on 3 primary areas: concept design, design selection, and design evaluation. We will see how each stage leads to the development of an optimized automated water tap control system. Our approach was guided by an existing patent by Swan Wolf Company, which informed our choice of component. We analyzed parameters such as microcontroller type, sensor specific, power source, and actuator model. We explore various alternatives for each component, considering different microcontroller, sensor, and actuator, and evaluate them against our data to ensure the best combination of functionality and cost effectiveness. Here we also detail our component option from power source like turbine or batteries to actuator such as solenoid valve and servomotor. These options were tested for the compatibility and performance based on our literature review. So concept design 1 uses the Arduino Uno priority and ultrasonic sensor for distance measure, controlling a DC water pump powered by the 9-volt batteries. The focus here is on reliable sensing and efficient power use. In concept design 2, we switch to a more compact Arduino Uno Nano and IR sensor for detecting percent. It's powered by a power bank for compatibility and uses solenoid valve for water flow control. Last but not least, our final concept design 3 employs a Raspberry Pi for sophisticated sensor data processing using ZX distance and gesture sensor for intuitive user interaction and servo motor controlled by the Pi to adjust the water flow. That concludes our visualization where we have showcased our systematic approach in designing and selecting the optimal component for our automatic control system, each with a unique set of advantage. Thank you.
Moving on to the decision-making process. In this part, we conduct an evaluation for all three concept design as mentioned before. The proposed design will be fabricated according to the best concept design after a thorough evaluation. The design will be assessed using a weighted decision matrix or a pure selection matrix. Moving on to the evaluation criteria, the selection criteria are chosen to align with the essential aspect necessary for a design with the best specification. The design selection criteria, we have three design selection criteria, which is the accuracy of components, the power efficiency, and the cost-benefit analysis. The first criteria are the accuracy of component. This criterion is based on the ability to detect user presence and constantly distribute water and achieving high reliability and precise. Next, the power efficiency factor. The significance of evaluating power efficiency as a selection criterion cannot be overstated. This is due to the power efficiency directly impacts the system performance, operational lifespan, and environmental footprint. By prioritizing power efficiency during the selection process, designers ensure that the system can function optimally while minimizing the energy consumption. Furthermore, in scenarios where access to power source may be limited or intermittent, such as in remote location or during power outages, an energy-efficient design becomes even more critical for maintaining continuous operation. Therefore, by incorporating power efficiency as key selection, it is vital for the design itself. And moving on to the other criteria, which is the cost benefit. Evaluating the original investment against potential saving from water conservation offers insight into the economic feasibility of the system. Hence, considering this factor, such as the initial setup, maintenance expenses, and projected water saving, we can assess the long-term financial viability of implementing the automated tap control solution. Now we move to the pure selection matrix itself. As shown in the figure, the selection criteria have their own weightage to the design. This is due to the significance of the criteria towards the project objective. Hence, the higher the weightage, then it has a higher significant impact to the project objective itself. As we can see, the accuracy of component is way 5, while the other two criteria is way of 3 and 2 respectively. After a thorough evaluation, the first concept managed to accumulate the highest total score and total weightage score at 45, and followed by the second concept at 38 and the third concept at 38. the evaluation, the final selected concept design is as illustrated in the figure. The final concept design, which is the circuit design, consists of Arduino R3 as the main controller, the DC pump, responsible to control the water flow, and the ultrasonic sensor for the detection of hand in the proximity. And all this component is connected to a MOSFET. Thank.
So today we'll be discussing on how the system flow, how the automatic tap water system flow, which is the system block diagram. So here we start with the sensor reading the data, which is the duration of the water flow and the distance between the hand movement and the proximity sensor. If the distance is less than 8, the digital write will create an output voltage which is high and thus turning on the pump and water will flow in. But if there is no, if the distance is less than 8, the digital write will create or make an output voltage which is low and thus turning off the pump and water will stop flow in out of the tap water. So that is how our system works. So hello, for the next slide, we will be showing you how our PLC or ladder diagram works in real life or works using the Fiddler diagram. So I will start the video. See that with a simple push button, start button, the system will turn on and will start all the running of the pump and the proximity sensor. So here you can show we're trying to integrate in internal relay and a timer so that there will be no waste of water and the system will be more energy efficient because for this particular simulation we only place the timer as 3 seconds. So when the proximity sensor sense a movement, it will only let water flow in, or the pump will only flow in for around 3 seconds to reduce waste of water supply. Uh, Beside of that, we also trying to integrate how trying to integrate the counter, which is the counter that can measure the tank, the measure that every time water pour out of the water tap in. So as as you can see from the video, this is on the left side you can see the value of the variable as the water what we call as the water pour out, it will also measure the level of the water in the tank capacity. So when the water that reach its limit or reach the tank capacity limit, it will initiate the limit switch that will automatically cut all the system so that it will stop the pump and the sensor, thus providing or hinder from any component of the water tap-in from damage by over voltage or over current that flow through the system. So, okay, then moving to the next slide. Hai, kenapa ni Pirik? So for this part, I will be explaining for the ladder diagram system rung by rung. So for the first rung, we have the start button and the T1, which is the timer. It will be connected to a limit switch and a reset button, and they are also X and Z which also have its own variable that will be resetted if the reset button is pressed. So, for the first rung, it will create an output of panel lamp. Panel lamp indicate the system is on or activated. So we latch the panel lamp to make it continuously on or switch on. For the second rung, the panel lamp will create an output of pump that turn on the pump, the proximity sensor, and the proximity, and this will be also controlled by a timer which is set to 3 seconds. So it will make the pump or the proximity run between 3 seconds, and it will turn off the pump and the proximity sensor if there is no movement. So moving to the next to the third rung, it will also uh, be connected with T1 and a proximity sensor being the input. So the proximity sensor will always monitor or measure the distance between hand movement and detect hand movement. So it will also have X, Y, and Z counter, which is to measure the limit in the tank capacity. So by the end, the last output will be the internal relay that is connected to the pump. So thus, if the proximity sensor doesn't detect any movement, the IR or the internal relay will cut off the pump, but also making the proximity sensor always turn on or continuously running. So in the fourth rung or the last rung, we can see that we take the measurement instruction to measure the tank capacity and the Z variable. Okay, X and Z variable will be explained in the next slide and how the monitoring mechanism works. So that's all from me. Thank you. Okay, for the value of variable and calculation of pump rating. So uh, assuming that we use a pump with a 5 watt power and a max of 0.5 meter and F max is 300 liter per hour, we can convert the flow rate from liter per hour to liter per second and use the converted flow rate to find how much water is pumped in 3 seconds. Convert flow rate from liter per hour L over H to liter per second L over S. Flow rate will be which is 300 liter per hour is converted to liter per second will be 0.0833 liter per second. So thus, that will be the time with time to find how much volume for the duration of 3 seconds the pump is running that will dispense the water. So calculate the volume of water produced in 3 seconds of flow rate. We get 0.25 liter, which will be the Y variable for the counter, 0.25 liters. So every 3 seconds, 0.25 liter water will be consumed by the pump to will the pump will flow out the water which is 0.25 liter. So assuming we have the tank capacity is 1 gallon, so converted 1 gallon to approximately 3.78 or just 5 gallon tank capacity, which is 19, approximately 19 or 18.93 liter. So for the X variable, we have the what we call the accumulated value for each of the running cycle. The Y value, which is how much water will be dispensed per unit second per liter per second, which is 0.25 liter per second, and the final one, the Z value, which is we times the accumulated of X with Y to get the Z value of the overall. If and if Z is the same value with the tank capacity, it will turn turn on the limit switch to kill the whole system of the diagram or the circuit. So that's all from me. Thank you.
In this section, we will cover our application, focusing on the usage of automated water tap system in our daily life. We will see how the automated water tap system works and benefits the people. By implementing automatic water tap system, water conservation is greatly enhanced. Traditional tap often lead to the water wastage due to the forgetfulness or negligence. However, with the automatic tap equipped with the microcontrollers, sensors and actuator, water is dispensed precisely when needed and automatically ceased when not in use. This leads to the significant saving on water bill and promote overall cost saving and energy efficiency. Automatic water tap system also play a crucial role in promoting hygiene, especially in the wake of the global pandemic like COVID-19. The touchless operation of this tap minimizes the risk of bacterial contamination associated with the manual tap. By eliminating the need for user to touch the tap to activate it, the spread of germ from hand to the tap and vice versa is significantly reduced. This touchless operation helps the spread of the bacteria and virus, enhancing public health. And another important application of automatic water tap system is the enhancement of accessibility, particularly in the public place or facilities catering to individuals with mobility issue. Users with the impairment or those carrying objects find it easier to access water without physically turning the tap on and off manually. This improvement in accessibility enhances the overall user experience and promote inclusivity in the public facilities. In conclusion, automatic water tap systems have diverse applications ranging from water conservation and hygiene promotion to accessibility enhancement. By leveraging technology to automate water dispensing, this system contribute to sustainability, public health, and inclusivity in our communities. Ladies and gentlemen, today we have delved into the pressing issue of water conservation amidst global population growth and clean water scarcity. Now let's wrap up by emphasizing the importance of adopting automatic water tap powered by Arduino technology. Firstly, we acknowledge that water conservation is paramount in our daily life. Given the challenge posed by the increasing global population and clean water scarcity, automatic water taps equipped with the Arduino technology present a compelling solution to address this issue. These innovative devices are programmed to dispense water based on the presence of hand, ensuring controlled and efficient water usage. By preventing excessive water consumption and fostering mindful water usage habits, automatic water tap play a vital role in promoting water conservation in everyday activities. The implementation of automatic water tap in various settings, including household, public restroom, and other water-intensive environments, hold immense potential to significantly reduce overall water consumption. This proactive measure contributes to alleviating water scarcity issue and safeguarding the availability of clean water for essential human needs. In conclusion, embracing automatic water tap powered by Arduino technology offer a practical and effective solution to promote water conservation in daily activities. By integrating this innovative device into our water usage habit, we can collectively reduce water consumption, preserve water resources, and contribute to a more sustainable future.